Okay, let's go ahead and get started. This is, to me, is really kind of a culmination of a lot of work with people here at Moorhead, with people at Sonoma State University. I wanted to introduce Dr. Garrett Jernigan. He's an astrophysicist from MIT. We're very fortunate to be able to work with him. And he's been working on this pocket cube, which of right now does not have a permanent name. One of the things is the trend, or the kind of the rule is you name the satellite after it gets up and after it gets working. So we're going to try and solicit from all the students here a name for this. Right, yeah. So let me. Good name, I'm hoping he's going to give us one. So let me, tell you a little bit about the why a pocket cube. And what you need to know is what we're doing here. This is the first of this pocket cube being built to launch. The concept of the pocket cube come up around 2004 or 2005. And the reason it come up is by that time we had been launching CubeSats, and then people started thinking they were really cool, and so they raised the launch price on us. And the reason we went to CubeSats to begin with was to get the launch price down where a university could afford to do it. So I decided, well, if you have to go smaller, let's do that. So I decided, well, instead of a 10-inch or a 10-centimeter cube, how about a 5-centimeter cube? And what we're looking at is, can we take, if you divide a 10-centimeter cube up into 5 centimeters, turns out you get 8 of them out of it. And could we pack those together to look like a CubeSat and get it launched? So that was the whole idea behind that. And it's went quite a while not even having a name for it until a friend of mine and I were sitting at a restaurant in Palo Alto with our wives having lunch, and we said, we got to name this thing, and what you want to do is name something in the name that gives you a size. When we named the CubeSat, there was actually, it was a cube, that told you about it, but it didn't tell you how big it is. And we said, this thing is big enough to stick in your pocket, so let's call it a pocket cube. And so if you look on the internet and look up pocket, C-U-B-E, somebody else has got it, somebody's doing something with it, you see all sorts of things for it. So we said, well, let's be a little different, so let's call it pocket Q-U-B, not with an E on the end of it. And so that kind of stuck. That's what we're doing it to. Then it turned out that a fellow over in England decided he wanted to bring up a website, and he got it before we did. And so we could not get a website with QUB. He had it. And so what we did is decided, to heck with that, we'll put an E on the end of it, and that wasn't taken, so that's where that'll come from. But the whole idea here is I wanted this thing, from my standpoint, was low cost. So if we make it small, we make it light, can we get it launched for a lower cost? That was the hope of it. And I wanted to have it so it was easy to build, very simple. And because I knew that we were not going to get much power off the solar panels, I wanted a communication system that communicated in Morse code. The ham radio guys have been moaning and groaning for years that all of the young amateur people don't learn Morse code, and I have to tell you, I took the test several times and flunked it, so I'm not, I'm like the rest of you. So, but I wanted to have it in Morse code, and that simplifies the radio, it simplifies a lot of communication with it, a lot more people can listen to it. So, today, this is the first pocket cube that's going into space. It's going to leave here on the 17th, and it's going to Rome, Italy, where it'll be packaged in the Unisat 5, which some of you have seen out here, and then it will go to Russia, and is to be launched on the 21st of November. Now, what we do is we don't put up any announcements about it until Garrett says, yeah, I heard it, it's working, and then we wave all the flags. if it doesn't work for some reason, and there's a ton of reasons. Yeah, there is a ton of reasons why it may not get in space, may not work. So, you know, that's really a difficult thing to do. So when it works and Garrett declares it's working, hopefully as much as he wants it to, then we'll declare a name and we'll tell everybody about it. But this is a new class of satellites. It'll just be called Pocket Cube, where the other one was called CubeSat. You know, they have the sizes according to the weight, and a pocket cube is supposed to be less than 1 kilogram, but now that weight has crept up, and they're launching CubeSats that 1U weighs 2.5 kilograms now. So it went in from the picosat class into the nanosat class, and I guess we're moving up into the picosat class because we're more than 1/10 of a kilogram. Okay, so this is, again, built by students here. We've had a number of students here working on it. Had Will, people have worked on the solar panels, right? Did you get to work on the solar panels? Yeah, you weren't sure what they were for. And so we've got a number of students here that have worked on this. So it is a combination of the two schools. The other thing about it is that it has some really unique things in it that have actually not been in any satellite before. And one of them is a new programming language called MicroLogo. And MicroLogo will allow students that don't know C programming to program this thing in a very simple, plain language, and that's what it's all about. And then the other thing is it'll transmit at least in two modes, a Morse code mode, and it will transmit in a packet mode. So I will let Sean McNeil and Garrett here take over and tell you about this. But this, to me, is a very... It's one of these times when you have these projects that, you know, you're kind of setting on pins and needles, waiting for the thing to go, waiting for it to fly, and it's kind of like, oh, they're going to launch it. I'm going to go stick my head under the pillow. I don't know what's going to happen. You know, but it'll be cool because what you hear, the sound that you're hearing today, is the same sound that we'll hear in the ground station when it comes overhead at 700 kilometers. This sky is high, much higher than we would like it, but it's high.
Thank you, Bob. I can't possibly tell you about all the people who've worked on this. It really is a bunch of students at Sonoma State, a bunch of students here over a 2-year period, and it's highly informed by all the work on CXBN, which is another whole set of, 15 students, Ben, or something? So it is a huge, huge building up of capability to get to this point. So I'm not going to try. I haven't even had time to make a slide that shows everybody. I apologize. I'll have to do that, for the talks later. So I didn't know what I should do today, because there's so much I could talk about. But I decided that since the thing is here in final testing, that I would just bring the satellite out and show it. Even though I was a little nervous about rolling it down the hall, I decided that if Bob gave me a tea cart and I weren't carrying it, it would probably be okay. So I think it was pretty safe. If it can, if it can't survive the roll down the hall, it's probably not going to survive the rocket launch. So I figured it wasn't that much of a risk, and so we're actually testing this thing and doing things to it that we have never done before. So the MicroLogo is something we've also spent a lot of work on in the past year to get it in here working. We started working on the MicroLogo for the next try of CXBN in the future, and that's quite far along in the other room as well. But this gives us a chance to test out the idea on orbit, make sure it works. So inside of here, actually, where's the inside thing? Oh, good. Yeah, okay. Here's what's inside there. It's a copy of the flight system. So this board is just sitting inside there, and the solar panels on the outside of the antenna. And I have a story to tell you about these little wings it's got. Drag wings. I don't know what to call them, but anyway. That's got a little story behind it. So here we've got the radio, That's the radio right there. Produces a tenth of a watt. Our resident expert is Will Roach back there. He knows all about these radios. He started working with Brian and I on this, 2 years ago, Will? Mm-hmm. And so he knows all about how to run this guy. Here's the magnetometer, okay, which is a okay magnetometer. It costs $35, I think, maybe $35 or $45, I can't remember. We have a much nicer magnetometer in CXBN that costs $700. But, Bob and I wanted to use cheap parts that, students could pay for this. So this whole thing in parts probably only cost, I don't know, $300. The board was made by a student. That includes the etching and everything at SSU. So we didn't even hire out making the boards. And it's pretty easy to have boards manufactured. And the people here are pretty much experts at doing that. And so you'll see that the boards you see in the other room are much nicer than this one. Okay, but that wasn't the reason I did it, because Kevin Zach, who did this, he knows how to order boards, but it takes 3 days. 3-hour turnaround, guys. So if we had a problem, I said, this isn't going to work. He could make me a new board in 3 hours. That made a big difference. We might not be here with us today if I had to wait 3 days. And then the weekend doesn't count. We work on the weekend, so it could be 5 days. That's kind of a little bit about the story of how this got built. Now, there's also a little connector here to take a CZT array, which is a particle detector. And we just didn't have time to debug all the software for that. We didn't all work. So I gave up on having that for now. I was kind of hoping the Italians would delay the launch for 2 or 3 months, because they've already delayed it for a year. If we had another 2 months, we probably could have gotten the particle detector on here. But so eventually we'll do it again. I lost the mic? Yeah. Where's the clip? Oh, it was on my collar. It was on the floor.
No, the clip's still on your collar, isn't it?
Yeah, I understand. I didn't realize the mic had fallen off.
All right. Here. Where's the clip?
Is it on my collar?
On the collar. All right. Maybe you could sing while we're waiting. Okay.
I got to practice my eagle call. Okay, so this I'm making this story really fast. I'm cutting off a lot of corners here and telling you very little about it. It's a long story about all these parts and how they got done. And I've been working with Ben for many years on getting these CZT arrays to work. A student here named Luke, who's no longer here, actually wrote the software to run the CZT array. And I'm sorry that we're not going to be able to get that in this time around, but we'll get it in the next one or the next one. We'll get it up one way or another. And every time we do it, we build on what all the students did previously. It builds up. So it wouldn't even be fair to just list the students who built this particular thing, because I'm very indebted to all the students in the previous generation effort. And I think that's what's really exciting about the whole SSU-MSU partnership, is that it's a continuing contribution by students over the years. I'll bet by the time Ben and I launched what we would really like to launch later, I'll bet we'll be up to 100 students that help make it really. And I have a rule about students that work with me. If you help do it, you are acknowledged for life. I don't forget you if you go off somewhere else and you can't work anymore. I still want your name up on the slide saying you made a contribution. And that would be true, Ben and Bob, also for acknowledging the CXBN students. If I give a talk about this, their names are going to be up there as well. And I've told Sean that. Sean spent the summer with me, but he graduated and has to go get a real job. And unfortunately, I don't have any money to pay him. If I had the money, I'd hire him myself, but I don't have it. But he will be acknowledged for his contribution, in perpetuity. I particularly like to do that for students, but I also think the staff here as well. Same goes for the staff at SSU and here. I mean, Steve Anderson is the guy that help us at SSU a lot. But there are a lot of people here on the staff who helped a lot too, and I want to acknowledge all of that help. In the science world that I live in, where you do big satellites, it costs a lot of money, people usually do not acknowledge the students and the staff. And it's something that I've disliked my entire career, and I've even complained to people about it. But when the scientists get up and give talks, they just ignore the engineers and the staff that built the bird. They tend not to do that. Now when the engineers go off to the aerospace conference and explain the satellite, they leave the scientists off. It's a little bit of a mutual agreement. But I like to acknowledge everybody who contributed. So let me just go forward. And I didn't know what to do here. So what we're going to do, I don't know what we're going to do, okay? Because I'm going to demonstrate what this thing will do. And I'll probably think of something that doesn't work, okay? But this thing has a mode in it, an extra circuit that we've created for this, that after 25 hours, if the thing gets, you know how you're typing in your computer, right? You get that blue screen. How many of you guys have seen the blue screen on your machines? Right? Well, this isn't as complicated as a Windows OS or Macintosh OS. But yes, all computers crash. It's guaranteed. And they crash for several possible reasons. One is there's a bug in the code. And even if you test and test and test and test, you might do something that you've not done before, and there's the bug. All right? Or a cosmic ray might zip in there and hit the memory and flip a bit. It's called a single bit upset. And then the program gets around to that point, and it does the wrong thing. And if it ever stops sending us beacons, right now, those are the beacons on the screen there. That's live data. Every time you hear that thing go click, it's sending some data, and every line on the screen is a packet. And the different kinds of packets for different types of data. The TO3 packets for magnetometer data, which I'll have Sean explain in a minute. So this thing is running. This is in its flight mode. Sean and I went through and changed maybe a half a dozen numbers yesterday, sort of not changing code too much, right, but changing some numbers, right? You know, how often the beacons come out, things like that, for final configuration. And one of the things I really wanted to have was Morse code, but I've had no time to do the Morse code, to work on it. So, you know, just never got to it. It was too hard. So what happened to Jordan? Jordan was here earlier. Where'd he go? Anyway, Jordan knows all about the Morse code with these radios. And so I said, Jordan, we only got one evening left. Last night he came in at 9 o'clock. I said, let's take a shot at putting that Morse code in. Okay. So we sat there, and you know, Sean and I were doing stuff and testing things, and he had to hang out for an extra hour listening to us jabber on about magnetometers. I said, don't go, we'll try. And so finally we got around to trying about 10 o'clock. And okay, show me your code. And he said, do this, do this. I typed that in, do this, do this, do this. And I fired up the thing. I had to change the frequency so that it wouldn't interfere with the test of this. So I had to change the frequency of the radio for the test case on the other thing. Worked the first time. In fact, that is so rare, I cannot tell you. I mean, we had no discussions about what his code was. I said, look, there are 35 radio parameters here that you initialize it. He said, you don't, just ignore those. Send these 4 commands. So we made a word called turn on the carrier, turn off the carrier. Then I said, dash is turn on the carrier for 30 milliseconds, turn off the carrier. Dot is turn on the carrier, turn off the carrier, wait 18 milliseconds. Then I made a little word called send a K, right? So I said 2K dash dot, whatever it is, right? Because that's the first letter of Bob Twiggs' call sign. We put in the first 3 letters, and I said, let's test it. Worked the first time. Now the problem is, I don't have that code in here yet. So I can't demonstrate it for you unless I run the other guy. So I was trying to get it done this morning so that I could actually have it coming out every time. How many people in the room would be able to read the Morse code? Anybody? Ben's a ham, that guy's a ham, Bob's a ham, I'm a ham. Nobody knows how to read Morse code, huh? How many people know what Morse code is? Okay, so if I send it real slow, right? Dash, dot, right? You can just sit there and write it down, dash, dot. Then you can look it up on Google, and right? So I'm sorry Jordan's not here. I thought he was going to hear this. But anyway, we're going to have it. But I mean, it's a little bit breaking my rules because I've got to go put it in tonight. And so that means we need to test more. So Sean's going to have to keep testing after I leave. But I think we'll put in the Morse code. And since we can send any commands we want up to the bird, we can now send up anything we want to send in Morse code. It's not going to be stuck just sending Bob's call sign. We can send anything we want by sending a command and saying, now start sending this. Okay, so that's a fun thing. So the other thing we can do is as this is spinning around, it's in the Earth's field, magnetic field, right? This magnetometer that I showed you. can see that changing. In fact, you could point that out, Sean, where that data is. Do we have it up there? I'm not sure we have the magnetometer up there right now.
Yeah.
Is it number 1, 2, or 3? The TO3 packets are magnetometer data. Yeah, here they are. Look, you see these numbers here? 1, 2, 1 like that, and then you see these big numbers like 65,000. Well, those are just negative numbers. It's just not printing them out as negative numbers. So you can see the magnetometer as this thing's spinning around. It's taking a sample every quarter of a second. So you see the field change positive and then negative and then positive, right? There's magnetic field. Well, that field's also in the room with us right here, right? So we can test this right here in the room. And then Sean helped me make a Fourier transform program that actually does a Fourier transform in the flight, finds that frequency and tells us what it is. And that answer is where, Sean?
That would be...
We just need a TO. Where's our TO? You need a TOO packet, right? Did it actually work?
Of course it would.
Let's pick one that line didn't work. I don't know
That's it. 484.
Where is it?
The one that I highlighted up there.
Oh, you highlighted it. Oh, okay. 484, 4.84 seconds. Okay, is the period of this thing. I think that's about right. Somebody could time it for me, but it's about 5 seconds. So actually, just for fun, I'm going to speed this thing up. Let's see if it gets a different number later. Okay. All right. So that's one of the main things we want to test. Okay. So we can measure the magnetic field. We can see the spin. Now, when it's in space, it's not going to just spin. It's also going to do this. You know, like you have a top right on the floor. It does this, right? This motion is slow. The spin is fast, right? That's just like a top. How many people have a top that you've played with, right? Except that with a top, it's the gravity that's making it precess. It turns out that in space, the objects are under what's called torque-free precession, which means it'll also do this, slow and that fast. So Sean has a thing that finds the spin, and then he looks at a longer periods to find the precession. Now, it's not precession now because it's not in space, right? So we can't. That's not going to work. So I haven't yet come up with a good way to test that, but I'm pretty sure it'll work. So once we know how it's wiggling in space, right, where it's pointing and spinning, right, we have a coil in here. You can put a current in it, and you can push against the Earth's magnetic field, and then you can make it move around on the sky and point in different directions. And you can take that motion that's going like this and damp it down. See, so what you have to do when it's going like this, right? You turn on the coil and torque it that way, and then it goes around half the end. The other side, you always push it towards the center, right? So it'll just slowly spiral in to where it'll only spin. This is a capability we need for our future satellites. We got to be able to point the detector at an object on the sky, either the sun or an X-ray source, or point it wherever we'd like to point it. We need to learn how to do that. So this can prove out that technology. So what happens if you do the torque to the wrong time and get the signs backwards? What happens? See, if I'm like this, see, and I say right at this point in time, go that way, and then right at this point in time, go that way, so the circle gets tighter and tighter. What happens if I get the sign backwards? It's going to get bigger and bigger. Suppose if I make it really big, like 45 degrees, they call that a tumble, right? That's called a tumble. So sometimes when you're launched off, you start out with a huge angle, but it's the same thing. Engineers just like to call the large angle version a tumble, and they call the small angle version a precession. It's exactly the same motion, right? So the detumbling algorithm is the same as the knock out the precession algorithm. So we can do that too. Okay, so let's do something that we haven't done before. I'm kind of making this up on the fly, so it may not work out. There may be something wrong with it. So we need some volunteers. We need, not Will. Will knows how to run the code. It has to be somebody new. Somebody new has to help. But I think, because of a story I'm going to tell you, I think I'm going to pick the first 2 volunteers. Is everybody okay with that? Does anybody not want to be picked? Does anybody have a problem with not being a volunteer? It's really not being a volunteer if I pick, but we're going to ignore that. Okay? I'm not calling you a volunteer, but is there anybody who doesn't want to volunteer? Raise your hand. All right.
Raise your hand for anything.
And we're going to let everybody have a chance to send a command. I mean, everybody's going to get a chance. These are just the guinea pigs that get to go first. If you want to, everybody gets to come up and send a command to the satellite. Okay? So I'm going to pick, I think I'm going to pick Professor Malphus and Professor Twiggs. Okay? So you guys come up. You can stand here. You can stand right here. Okay? Where did I put that piece of paper I wrote? Here it is. Okay. Okay, here are the roles. Okay, and this is the way this is, it's a little bit of a fun thing, but it's got a serious point to it because I think it's really true that when you command a satellite, it's really a good idea to always have two people, especially when it's 2 in the morning and you've done it for a while and you're cocksure that you know what you're doing. It's always good that you have another student with you because you guys are going to, I mean, as far as Ben and I are concerned, and Bob, we want you to run this thing. I mean, I'm going to send the first commands because I'll be nervous, but once it's working, I want this. My job is to put myself out of business and turn it over to you. Okay, and I don't. You have to work with Professor Malphus about and Professor Twiggs about who gets to do it, and who gets the 2 a.m. shift and who gets the 2 p.m. shift. Right? You may have to fight over what time you get to come in because the satellite flies over when it wants to. It doesn't care whether you're having dinner. All right. Okay. So the idea is. Bob is the engineer, so we're going to let him send the command because it's not a good idea to let scientists send commands. I've never been allowed to send any commands to a satellite because I'm a scientist, and scientists love to play around and do stupid things. But a good engineer will always protect you from a stupidity. And that would be like Bob or Professor Kruth or somebody like that. So let's let Bob do the typing because he's the one that's going to have to decide what to do. Now, Ben is going to decide what to do. What to do. But I'm going to give him a suggestion here as a fellow colleague. I've got a suggestion on this. He's not going to tell you what it is. He's not going to tell Bob what it is. Okay? I'm giving you this, okay? Okay. So this is what we're going to try this out. And then Ben's going to decide whether he thinks it's a good idea not to do this command. Now, normally he ought to look over the code. He should have practiced last month, and he should have understood everything, so he would have some way to judge. But maybe he's going to trust me and let it go. But we're fellow scientists, so he's going to have to think about it. What?
Beacon, transmitter, or all the
You actually want to know what it's going to do? That's not fair. I'll tell you in a minute. Okay.
So we'll do it.
Okay, but I'm suggesting that you send this. Okay, and then once you and I confer. Then you, as the responsible person, will make the decision whether to send it or not. I'll be gone. I'm gone. You're the responsible party. But we can consult, and I can answer your questions, right? Okay. You can make a judgment, right? Yeah. But you're not going to send it. You're going to hand it to Bob. Right. Now, Bob is going to independently decide whether he wants to send this command or not. He can overrule you and you, and not send it. He needs to know that is it okay to send it? Now, we have a little advantage today. What's the advantage that we have? We have a very important advantage.
It's on the ground.
It's on the ground. If they break it, I can still fix it. Right? If it were on orbit, I wouldn't let them be doing this. Okay? We'll see. But then we're practicing. We're pretending like we're on orbit. So we don't have to do it exactly this way. You guys can make up your own procedures. But you really ought to at least consult with one other person. And whatever you're going to do, you should have practiced it on the ground copy the day before, right? Just see what's going to happen, right? But really, when you're in the room with one other student and you're in charge, I mean, you can call Ben in the middle of the night and wake him up, or you can decide you know what you're doing and send the command. I know what Will would do. Ben would probably like to have the sleep. Okay, so this is a fun thing, but it's a serious thing too. It's making a point. Okay, so ask me some questions.
Okay. In front of the whole group?
Yeah, tell me your concerns or whatever you have.
Power system or
Beacon.
beacon? Okay. Beacon mode or beacon power?
Beacon mode.
Okay. Interval or modulation?
Neither.
Okay.
I mean, it's a little unfair. It's kind of interval, but
Yeah.
but it means it's not going to do it, so there's no interval.
Right. Okay. Okay, I'm good.
That was quick. That was pretty quick. If it were in orbit, he would have asked more questions if it was in orbit. He knows it's right here, so he's pretty secure. So now you can give it to Bob.
All right.
Okay? So you read it, Bob. Read it out loud to everybody.
Okay. So CSR, left square bracket, ALL underscore OFF right bracket.
Right.
Correct?
Okay, don't type it yet. Let's have a discussion. Okay?
Should I type it?
Let's think about it, but let me tell you what it means before we do it, okay? CSR means compile, send, and wait for the response. Compile, send, wait for the response, whatever code is in brackets. And the word in brackets is all off. Okay, that could mean turn off forever, never talk to me again. That's why Ben asked the questions. It's not even the power system. It's actually just telling the radio not to send beacons. Right? It just means, see these beacons here that are coming out? We're just saying, don't send those anymore. Right? Pretty safe. It doesn't mean all off, meaning shut off the battery and shut down and never talk to me again, which is something the FCC requires you to be able to do, actually. Okay, we can do that, but I'm not going to tell anybody how to do that today. Okay? We can do it. We can brick it. Okay? We can brick it if we need to. Okay, so now, it's Bob's turn. He can ask the class to vote, but it's on him if he sends it. It's not on Ben. It's not on me. He's at the console. He's typing the command. It's totally his responsibility. He cannot shirk it. It doesn't matter what we think or anybody else thinks. He can ask our opinion, and he can ask me questions. But basically, when he hits the return, he can type it in, but when he hits that return and sends it, if you're the operator, you are 100% responsible for hitting that return. So if you feel like, geez, I didn't practice enough yesterday, I'm not really sure what's going to happen, right? Then you should wait. So let's do it tomorrow.
Okay, is there a space between
Yeah, there's a space between the CSR is a ULOGO word which must be separated by every other ULOGO word by a space. Okay, brackets are different. So you couldn't say CSR left bracket without a space. But inside the brackets, you don't absolutely have to have the space. I just recommend you put the extra spaces in. So go ahead and type it. Oh, wait, one more thing. Let's see. You got to stop it from sending packet. Already stopped. Okay. So he typed star, stop, star. Did we see that? Here. Okay. That's not a flight command. That just tells the ground computer to stop printing out the packets. So that's a very safe thing to do. So now we're going to type it in. CSR, left bracket.
Why are we sending this command?
Because I want to turn off the beacons. Well, partly I just want to show you how it works. But one of the reason I'm doing it is because I want to turn off the beacon so we can send a bunch more commands and not interfere with the beacons. We want to get it to shut up so we can do more stuff. So otherwise I got to sit there and time it between the beacons and all that. Because if we send a command at the same time we're getting a beacon, it'll screw it up. Neither one will work. Right? Okay, what do you think?
This finger.
Is he going to do? Should Bob do it? Now wait a second, guys. Before he does it, does anybody have a question and some advice for Bob? Question and advice. What?
Oh, I do that all. So is your opinion I should send it? Yes.
Yeah.
Give me a opinion.
Do it. No, you have no responsibility. It's all his.
You authorize me to send this command? You have no responsibility other than authorizing it.
You are authorized.
Am I authorized?
Right?
You're going to be able to turn it back on after you turn it off.
Not necessarily. Not necessarily. We don't know that. I've never done this particular demonstration. It may kill it forever. Now it's still in the room, so I could probably fix it, but it's in orbit. No, I don't know. This software has only been in here 8 hours. How do I know there's not a bug in it? It may not. I mean, I'm going to be really sad, guys, if this doesn't work. But the answer to your question is, I actually don't know. I really don't know. Now, Bob is shaking a little bit now. Now, wait, one more thing, Bob. Because we're going to turn off the beacons, you need to wait between two beacons. So you got to listen, right? Turn it up, and listen to the beacon, and then they come every 20 seconds. So a few seconds after that beacon comes in, you hit the return.
Attention.
Command goes up, answer comes back. Okay, this is an 888 packet. This is the spacecraft clock. This is a checksum. And this just means I got something and I did it, because we won't necessarily be able to hear that radio. Now what's going to happen now that's different, if it works? What do you think is going to happen? Ah, you're right. How long do we have to wait before we know it worked? All right, let's wait. Let's wait 40. Bob would probably wait a little longer, but he's an engineer. Ben and I might be able to wait 22 seconds. Then we would want to take action. I think it worked, right? I think it's already been 20 seconds. But I understand. That's right. Sometimes the radio doesn't work good, and so in a real situation, you want to wait a little while and see if it really took hold. So the advantage of this is now we can send more commands. We don't have to worry about this getting between the beacons, right?
Can I turn the beacon on by saying all on?
You could.
We should try.
Or do you want to go in and do something more dangerous first? Well, I don't know, Bob. They want to do something more dangerous, but you're in charge. What do you want to do?
I want to be conservative.
All right.
I would turn it on. And
Turn it back on and then back off again. How about that? Okay, we're going to do something a little more complicated, okay? So type the following, Bob, but don't hit return. Okay, type CSR, left bracket, space, all on, all ALL_ON. What?
Stop.
Oh, you got to stop the thing first, yeah. You got to stop the ground so you got to do the star, stop, star. That's not a flight command. That's just telling the ground computer, I want to do something. So the star, stop, star is a perfectly safe command. Does it say stopped? What did it say here? Stopped. Okay, so that means it'll listen to you. Okay, now type CSR left bracket, but don't hit the return, Bob, until I tell you something else. I'm making this up on the fly, but go ahead. So all on, space. Yeah, we want to do some more things. Space, on. I think you could hit a 0 there.
yeah.
Got the 0, not the O. I should have Yeah, go ahead and try it. Close the bracket and do it. Close it and do it. What do you think is going to happen? No, a right bracket, not a curly. Okay, let's just do it. It's okay to do it. Try it. And define. If you misspell something, it's not going to hurt anything. All right, do whatever.
Unless you misspell it and it's not command.
And it's a secret command to break the satellite. Come on in, Jeff. We've already been talking about you. Your ear should be burning. All right, all on, but wait a second. I want to add some more. Take away that white bracket, okay? And let's say wait for 2 minutes. Let's see, wait. Wait 10,000. No, we got to wait. 2 minutes will require us to wait. Okay, so say repeat. Repeat. Space, 120 seconds, 120. Space, left bracket. Left bracket, not right. Left. Space. Wait 1000. MWAIT. Millisecond wait.
So 1 second.
Space 1000. That's 1 second, right? And then space right bracket. Space. All off. All underscore off.
Okay, do I need to have matching brackets?
At the end. So type all underscore off, and right? ALL underscore off. Right? Right? Space right bracket. Don't hit return yet. Okay, who can tell me what that's going to do? It's going to turn it on and wait how long? No. Repeat 120 times.
It'll go for 2 minutes.
2 minutes. And then it'll turn it back on. Okay, this is the important thing about the satellite. That is a one-line program. We're going to compile it. We're going to send it to the satellite. It's going to execute it and tell us that it executed it. And we can tell because we'll hear the beacons come back on in about 2 minutes. Right? We'll turn them on, and after 2 minutes, they'll stop coming. Right? Okay? There has never been a satellite ever built that's done this. Not a $1 billion satellite, not a Mars rover. This is the only satellite in the world that can do this. As far as I know, no one's ever made a satellite where you can write a program. This is logo programming. Will can attest that there's nothing unusual about this line of code than all the other flight code. No one's ever had a satellite, a spacecraft, where you could do this. Because we're going to compile that code, send it untested to the bird. It's going to execute it and do the job, do what we told it to do. So any code that we have in the satellite that we've ever written is a command. You do not have to make a command system. You just have to know how to write the flight code, and then you can make up something like this on the spot, right? And do it. So this is a unique thing about this. When I say something's unique, I can't really say that for sure. Everybody I've ever asked this, every bit of satellite, I ask them, could you do this? And the answer is always, so Bob, this isn't just uploading new code. It's beyond that. Right. You can also upload new code, by the way. But this is like the way you command it is you write the code, the ground compiles it, sends the executable code to the flight, and does what you said. Okay, so before we do it, the all-on's going to happen pretty quickly, right? And so we're going to wait 2 minutes. So it's going to be about 2 minutes, right? Beacons come every 20 seconds, so we don't know exactly what the phase is, right? So it's going to be about 2 minutes. They'll stop coming. They'll come for 2 minutes, so we should get 5 or 6 beacons, right? All right, I'm ready. Do it. I can't tell him to do it, by the way. He has to want to do it.
Go in.
Point up. Now we're not going to, it's going to go 2 minutes, right? But we should see some beacons come back on, right? Hopefully not more than 20 seconds, guys, or something's wrong. Is it going to work, John? What are you wrong?
Because it's in the middle of that. Yeah, it's repeating on top of the beacons. Although, shouldn't it send a confirmation?
You're right. You're right. He's absolutely right. So here's my mistake. It's not going to hurt anything.
Right.
But because it's sitting there twiddling its thumbs for 2 minutes, it's not going to be able to send the beacons. So we're going to change it. But we'll let it go anyway, because it's going to tell us when it's done. It's going to send a TO4 when it gets to the end. So how do we need to change it to make it work? So we can tell that it's working. Why don't we just put a send beacon packet instruction right in the list? Why don't we just include the send the beacon right in there? Right? We can just say send beacon packet right in the middle of the command, and it'll send one. Right? So this flexibility to do anything you want has some risk involved. Right? So how long has it been? Hit the up arrow, Bob. So it's my mistake. So let me explain the problem here, and Sean's right. When it's doing the 120 wait that it's busy doing that. It's waiting, so it's not going to be sending the beacons until we finish.
Could I go back in? Yeah, I can go back.
You can. You can edit it.
What's that?
You can edit it.
What do you want to edit to?
Well, let's put a send beacon packet in front of the repeat. So go in front of the repeat, and let's tell it to send a packet.
Right there?
Actually, let's actually do it a little bit differently. That's because the beacons came back. That's the end of the command. So that was the 2 minutes. So just do the up arrow again, Bob. Get it back.
Type it in again?
Yeah, the up arrow. It'll get it back. See, it sent us the TO4 after 2 minutes to tell us it did what we said to do. But what I thought it was going to do was send us beacons, but instead it sat there and just waited 2 minutes.
Every 2 minutes, or just that once?
But that just does it once.
Oh, because you told it to turn off after.
That's right. The end was turn it off. If I hadn't put the all off at the end, it would have come on. Let's try that first, Bob. That's a good idea. I like that idea. Let's just leave off the all off. So just do the stop, right? And then just say up arrow. You can just say up arrow. You can retype it, but you're stopped. You can hit up arrow and just get back to command. There you go. Now let's get rid of the all off. Do something simple. This is a simpler idea first. We'll do something fancy later. So now just put the right bracket. So that just says wait 2 minutes and then turn the beacons. The beacons will be on, see. We turned them on. We sat there, twiddle our thumbs for 2 minutes, and then when it ends, the beacons will start up. You're an engineer, Bob. You're not supposed to be impatient. Only scientists are allowed to be impatient.
You can make it 20 seconds.
It could. You want to make it 20 seconds so you don't have to wait 2 minutes? Now let's do 2 minutes because then we don't have to time it carefully. So you think it's going to work, John? Okay, go for it.
I want to change your 120.
Okay, there's the command going up. We heard it go up. Now it's going to wait 2 minutes. It's turning. The beacons are on, but it's busy. It's busy looking at the clock, waiting 2 minutes. So after the 2 minutes, because the beacons are on, there. That's just acknowledging that it finished the whole thing.
No, he secretly took a
Zero.
Oh, okay. So we only waited 10% of 2 minutes, right? And look what happened. The beacon came up. See it? There's the beacon.
Now, the thing of it is, we could sit in a ground station when that comes over and do that. And it's going to answer you back from space.
Oh yeah, now it turns out that this is only going to work because of Jeff and Professor Moffers and Professor Cruz have done an enormous amount of work in the last year to upgrade the dish up the hill so we can talk to this radio from 700 kilometers. And quite frankly, they don't like to hear this, but I think if they don't make that work, I think we're toast. Because this little radio is less powerful than a walkie-talkie that you buy from Radio Shack. But they fixing that. You've seen the dish up the hill. I'm sure Ben pointed it out. It doesn't normally work at these frequencies, and they found a way to modify it so that we can point at this satellite at 700 kilometers, and we can hear the signal, and we can also push a command back up. I mean, right now we're only going from this antenna to this antenna right here. We're going 6 feet across the room. It's not really a fair test, but I think it'll work. Okay, so the beacons are back on. So, Bob, if we want to do anything else, why don't we turn the beacons off again?
One thing, Dr. Jernigan, if you could explain very quickly, these guys are used to seeing all of the subsystems.
Yeah.
Totally broken out.
Yeah, I didn't talk about it very much because it would take me okay. Yeah, let me explain. Let me explain a little bit about it, okay? Because the CXB is more complicated. This is the radio, this is the magnetometer, and then the processor's on the back there, that little square, okay? Now, normally, I'm missing a piece here called the Doty Safe Mode circuit that has the charging system and the battery connections to the solar panels. I should have brought that out. I don't have it with me. It's inside of there, okay? So our equivalent to what Ben's talking about is just a little tiny board right here. Has a very simple system that has 3 NiCad batteries and a diode, and it just, okay? And it has this one smart thing, though, that if the battery gets too low, right, it's supposed to turn everything off and wait for the sun to charge the battery back up to a healthy voltage. So if we're doing too much stuff, running the coils, doing too many beacons, we run out of juice, it'll shut down, and it'll take maybe as long as 3 hours to charge all the way back up, right? And it'll do that automatically.
See if it sparks. Now, grab this last one on the end. The reason you get
Now wait! You guys are accepting responsibility now. If you're linked up, then you're responsible as much as Bob. What?
So one thing I'm not sure we've ever explained to these guys.
Go ahead.
is
Tell me,
that
Ben.
The basic subsystems on the satellite, EPS,
Right.
command data handling systems, the flight computer, attitude,
Right.
determination control, comm system, they're common to all satellites.
Including this one.
From a $1 billion defense satellite down to pocket units. They all have those systems. So
Now we cheated a little bit in the following sense. I don't have the power system board here, so in fairness, I just don't have it to show you because I only have one that works and it's in there.
yeah. But once
Okay,
you understand
it's a little board that sits right there that does the power and knows how to turn the payload on and off. That's the power system, right? Then this is the processor that runs the radio, but it also runs the magnetometer. In CXBN, that's a different processor. One for the radio, one for the, right? So we do everything with the one processor, but you could very easily make a version, one for the radio, one for the magnetometer, and one for the particle detector, right?
Yeah.
But because we had to do it quickly, and we didn't have a lot of time, we just had the one processor serve all the functions. In general, you don't. Like CXBN actually has separate processors for the radio, for the power system, for the command and data handling, and the science payload. So that's at least 4 processors. It may have a couple of other ones in there secretly, but I don't even know. It's at least 4. It's at least 4, okay? So that's kind of that's the pieces of the satellite. And students can work on any part. Go ahead.
You said that it shuts off like if it runs out of power.
Yes.
So does that mean that everything you were working on at that point in time is erased?
Yes.
You have to start over?
Yes.
That's nice.
But see, if the batteries are too low, it's going to die anyway. And if you take the batteries too low, it'll damage the batteries.
So how
So
do
you-
you know when the battery's too low?
Well, because the circuit looks at the voltage. Okay, where's the voltage here, Sean? Point out where the voltage. Battery voltage. You can take an old one. Here, TOO, 3.64 volts. Okay, so it starts out when it's fully charged, it's like 4.1 volts. It goes down to 3.6, and then it stays at 3.6 for a really long time. And then when the batteries are just about the tank is empty, right? It starts to make a sharp dive below, and then you know you're on the edge of like damaging the batteries if you let it keep going down. So when it gets down to like 3.5 volts, the circuit says, I'm turning the payload off. So if you have software in the payload that says, it looks at the battery and says, you know, it's down to 3.55, I better stop sending beacons and turn off my torque coils, then it won't actually go over the edge. And then you can let the sunlight charge it back up. But if your software doesn't do that, the safe mode circuit is going to shut you off anyway. So I answered you slightly wrong. If you're smart about it and you write all your answers into memory and you shed power and watch the battery voltage and don't send any beacons and don't use any power and let it slowly come back up, you could write a program so that it doesn't trip. But the safe mode is there because suppose you send a command and the thing starts just sitting there doing nothing. In a loop, right? That's the blue screen of death, equivalent, right? So the hardware will save you. Go ahead, Bob.
I want some students saying.
Oh yeah, we're going to do it. It's time. It's time. So, okay. Who wants to volunteer to go up for? Not Will. Will doesn't get to do it first. Who wants to come up and send a command?
All right, we got a couple volunteers.
Okay. You need 2, right? One for the button and one to provide the advice, and then you can switch roles and do another one. Right? Okay, so what do we want to do? Right now we're off. No beacons. Why? So no beacons is good. Why? We're going to do a bunch of stuff, right? So you don't want to have to be sitting there listening. There's the beacon, now send a command. This way you don't have to bother with that. What's bad about turning the beacons off? Why is it a bad idea? Well, why is that bad? You can turn it back on anytime you want.
Its job is to collect data and tell you if it works. No data.
Right, so what happens, it flies overhead for about 10 minutes. What happens if your antenna breaks or maybe Jeff's up there tuning it up and it stops working? And all of a sudden you say, oh my God, it's going to leave and we didn't turn the beacons back on. It's kind of bad, isn't it? Because then the next time it flies over, it's not going to be sending any beacons. Now you're going to have to shoot a command up to say all on blind. I'm sure that Ben would just sit there and just send it repeatedly until we get it back on. Oh, but you just sit there and move the antenna. You'd have to just search it, try it. Move, send, right? And it's a lot of work to have to do that, and it's very nerve-wracking, right? So you don't want those beacons to go off.
The bad thing about having a big dish is that the circumstance. Big dishes are great. They're almost better for the games and close the communication. The bad news is that the half-power beam goes as an inverse. So in other words,
You have to aim it better.
the beam is really tiny. So you got to know exactly where you're pointing. So I could be pointing the
Right.
degrees off and every.
So Ben, I think what we would do is we would take one of the Yagis, we continuously blast up the all on command and hope that it flies through the beam and gets the command, and then it'll start sending beacons again. But that's not a real good plan. That's a bad plan, but that's an emergency plan. Okay, so what do you think this will do? What do you think I put in to solve this problem? I put something in there. How long do you think I put in?
Maybe 10 minutes, 20 minutes.
15. Okay, so if you forget to turn it back on, let's just say you forgot, right? You do all your stuff. You say, oh, geez, I never sent the all on command. After 15 minutes, it will turn itself back on anyway. Now, have you waited 15 minutes since we turned it off? So I didn't want to tell you that because I wanted it to collide with somebody sending a command. Because it's happened to Sean and I. We've been sitting there like, let's do something, and then the thing will turn back on, and we think, oh my God, how did it possibly do? Oh, that's right, it's been 15 minutes. But we didn't realize that because we're talking and we're thinking it's only a couple minutes. Look at our watches. Oh yeah, it's been 15 minutes. Okay, we could even change that time. I could change it to 1 minute. We can send a command to say, wait 1 minute afterwards.
Can you turn the magnetorquer on and see?
It's on. Oh, the magnetorquer, yeah. We don't have the compass. You got to go get the compass. Go get the compass. Yeah, we can do it. We can do it. Okay. So look, enough talk. But if we wait 15 minutes, the beacons are going to come back on. And I don't know when we turned them off, right? I don't think it was 15 minutes ago. It's like 5 minutes ago. Okay. So what do you guys want to do? I won't mind if you break it because that way I'll know. Yeah.
Turn the magnetometer on, and then if we have a simple compass.
You mean the torquer?
The magnetorquer.
Torquer, yeah.
If you have a simple compass, you can see.
If you put a compass on the table here, you'll see the needle go crazy, and then it'll go off. And we have a command that'll do that, but we need the compass on the table to see it. But you can go ahead and do it anyway. I think it's called test-torque. I think it's going to turn on. It's going to turn on the coil, and I think it leaves it on for 2 minutes and turns it off. It's just a test command. So test. Now you got to do CSR left bracket test torque.
Would it affect a cell phone compass?
It would actually. You got one? Bring it up. It would work fine. Test dash. So put your thing in application in compass mode and just bring it up here and hold it near a satellite. You might not be able to get it. We could set it on the table there with it, I think. Now stop for a second. We'll embellish a little bit. In front of the test word, why don't we just print a number out? Right. Just so you can see that you're, sort of remind yourself. Make up a number, a favorite number, right? Right? Say F print. When you're in flight, you F print. You flight print. So say F, P-R-I-N-T. And then put in a 3-digit number after that. Just pick a number. Favorite number. You need the space. You need the space before the 117. Okay? And then let's print a number after we do the test torque, right? At the end. Now this isn't going to work like I was thinking, but at least we'll have an indication that this particular code was being sent. It's really going to send the numbers down after it's all done, but just go ahead and put another F print in. Print a different number. This way, if you're sending the command, you get some stuff back from the satellite. You were expecting these numbers, so if you don't get them right, then it did something that wasn't what you said. Right? It's a little bit of a way to check, right? So close it up. So that test torque, I could find the code for test torque, but I tell you what it does, because I can show you the code in a minute. But now let's put this compass of hers actually on the table. So I'm going to turn off the table for a second, so I can safely put the thing on there closer to the satellite. Now where's the switch, damn it? So, do you see it? Okay, there, okay. So we'll put this on here, like that. Okay, now turn it back on.
What's the compass say?
Okay, now the compass is actually spinning because it's tracking the Earth's field, right?
It says we'll put my
Okay.
So the point is, when the coil comes on, it's going to be stronger than the Earth's field, and it's going to interrupt the pattern. Okay, so let's do it. Just hit return. Oh, you got. I didn't tell you to stop. The star, stop, star. I always forget that. So just do star, stop, star. That just says listen to me. Right? Return, and then just hit the up arrow. You'll get the command back. Again, there. Okay. Are you ready? Hold on. Are you ready? You did it? I got the wrong name. What is it called, John? Test torque? What did I call it? All right. Here you go. We're going to have to look the code up, guys, which is an interesting thing to do anyway. This is what you'd have to do. Where did my glasses go? I can't do a damn thing. So we're going to look at the code that's in the flight, and we're going to see what the name of the word was.
Wait, that's not a CSR. That's an actual.
That's it. See, if I looked at the code, I'd see. I'll tell you what the problem was. The problem is I made a word called test torque, which already has the CSR in it. Right? So I wouldn't have to type the CSR. I was probably being too smart. So just forget the prints and just type test torque without the CSR. But that's just because the word test torque has the CRS command inside of it. Right? Try that. There you go. Now that's telling it to do it. It's gonna. I think it's. Did you see anything happen?
It's still following the
It's easier to wait for the off actually. So let's wait for the off. 2 minutes.
It's following the satellite now.
Is it?
Yeah, you can see the degrees are getting higher.
Well, because the coil's on. Right? So it's interfered. Now, in 2 minutes, it's going to turn the coil off, and then it'll go back to looking at the Earth. So when you want to get good magnetometer data, you can't have the torque coil on. Right.
Okay, we're at the end of the class,
Okay.
so if anybody wants to leave, they can.
Right.
We're looking for volunteers to go up the hill to deal with the feed removal. All right, so anybody who wants to come up the hill.
Let me pitch that. We need volunteers to go up the hill and learn how to feed.
Hold on. Let me just turn this off before you take it off. There you go. Now you can take it off. That's good.
Just by being there, you'll learn something.